extreme values are the same thing as maximums and minimums. So again, extreme values are maximums and minimums. In Calc 1, we figure out how to find maximums by finding the derivative, and then finding critical points first, and then testing whether the critical points yield maximums or minimums. So critical points happen when the derivative in Calc 1 is equal to 0, or when the derivative does not exist. So that would be an example of a maximum where the derivative is 0. Or we can have a minimum where the derivative, again, is 0. This is in Calc 1. Or we could have this situation where the function has a derivative of 0, but we don't have a maximum nor a minimum. In this case, we have a point of inflection. And we're going to have a similar situation in functions of two variables. Things are going to be somewhat analogous. Once we find critical numbers, we find the second derivative, and the second derivative can tell us whether we have a concavity down. So if the second derivative at that point is negative, we have a maximum. If the second derivative is, so we have a second derivative, in which case the second derivative is negative, we have concavity going down, concavity going up. So in this case, the second derivative has got to be positive. Yeah, and here, the second derivative is 0 because we have a point of inflection in which on the left of this point, in this example, the second derivative would be negative, while on the right, the second derivative would be positive. Yep. Okay. So before we start, let's talk about what we mean by local maximum and local minimum. Multivariable. Specifically, though, functions of two variables. So we have a z, which is a function of x and y, which is a surface. And we could have perhaps this kind of situation where we have a mountain, and then that would be the maximum. Or we could have going down, and that would be a minimum. Or we could have neither one. Oftentimes we have this kind of situation. Oops, I was getting out of my picture here. So this kind of situation where if you go in one direction, you go up, but if you go in this direction, then you go down. And that is what happens sort of on the crotch of jeans. You know, this is not necessarily the best picture, but it's like jeans upside down, so to speaking. But in one direction, we go up, different direction, we go down. So that is a saddle point, maximum, minimum. Now, we have definitions that are exclusive or inclusive for maximums and minimums. So we're going to use, so let me talk about that for a moment. So definitions could be inclusive or exclusive. So for instance, the typical example I provide here is with definitions is a square, it's a geometry question, a rectangle. And people argue back and forth, but the bottom line is it depends how we define a rectangle. So we can have a definition of rectangle that is exclusive, excluding squares, or we can have a definition of rectangle that includes squares. We can have it either way, depends on our application, I suppose. Most math people in my opinion, in my view, I think we'll go for inclusive. We usually go for inclusive definitions versus exclusive. Otherwise, when we make statements, we have to make exceptions sometimes when we have exclusive. So the only reason why inclusivity makes more sense is because when we write the statements, we don't want to have exceptions. I don't want to dwell too long on that, but um, so the problem here, well, it's not a problem, but something that we have to be aware of. If you have a sort of a cylinder, yeah, like this, a sheet. So does this happen where this line is totally horizontal? So those are parabolas, a bunch of parabolas going down. And this is a sheet. So is this point a maximum or not? Um, because points next to it are at the same level, are level with this point. And the answer is, because we're using inclusive definitions, yes, this point is going to be a maximum of the graph. So is this one a maximum? Okay, so then the next example, what about a horizontal plane? If you have a total horizontal plane, so all the points are leveled, is there a maximum? And again, because we're going to use an inclusive definition, yes, all of the points are maximum on a horizontal plane. And there are graphs, of course, that don't have a maximum or a minimum, or one and not the other. So for instance, if you have a paraboloid, so this keeps going up like that all around. This has a minimum, but it has no maximum. And I'm running out of paper, so I might just as well start a new sheet here. And we could have situations where we have two hills, one higher than the other. So this is a surface going on like this. Oops, there we go. So again, yeah. So there's two hills, one is higher than the other. In this case, both are local minimum, rather maximums. Both of them are local maximums. And this one here would be the absolute maximum on top of being, assuming that this was the entire graph, on top of being a local maximum. So this point up here would be both local and absolute. Or if not absolute, you can use global maximum. This guy, however, is only a local maximum. And the reason is because there's a disk at which there's no point above it. Yeah. Yeah. Again, it is not because all the points around it, close to it, sufficiently close to it, are lower, but because there's all the points around it are not up. I mean, sufficiently close to the point are not. There's no point above this point. All right, so that is the idea behind extreme values. How do we go about finding extreme values? We find equivalent to critical numbers. So in 3D or in Z, so the idea here is that we have Z equals f of x, y, and we want to find the equivalent to critical numbers. And they will happen, or critical points, and they will happen when the derivative with respect to x is 0, and when the derivative with respect to y is also equal to 0. So that is the initial way we're going to find critical values. That doesn't tell us we have a maximum or a minimum necessarily, because we could have different situations. We could have minimums, maximums. By the way, these points which are neither maximums nor minimums, none at all, these are called saddle points. Saddle point. Yeah, because it looks like a saddle of a horse, and that's a minimum. That is a maximum because there's no point above. The reason why this is not a maximum because there's a point right next to it. Of course, when I say right next to it, that doesn't make sense because real numbers are continuous, but that's an expression. So right next to it, we have a point that is above this saddle point. So that's why that is not a maximum. And here, there's no point anywhere around any one point that is higher. So every point here is a maximum as well as a minimum. And the reason is because we're using inclusive definitions, such as when we say that this square is a rectangle. Okay, so that is the initial thing. But then we have to test whether we have a maximum or a minimum. In Calc 1, the way we tested was with the second derivative. If the second derivative is positive at one point, then we have a minimum because this tells us something about the concavity. We have a concavity going up, concavity going down, consequently we have a maximum, and a change of concavity if the second derivative is 0, if we have a continuous function, of course. So what is the equivalent in functions of two variables? Okay, so here's the deal. We have to introduce the second derivatives with respect to x, second derivatives with respect to y, and second derivatives combined. So if f sub x, that means the second derivative with respect to x, multiplied with f sub y, second derivative with respect to y, is greater than only, not equal, to the combined derivative squared. So fxy times fxy. So if those two multiplied together are bigger than this one, which is going to be the same, this is, I suppose this would have come from xy and then yx, but most of the time those are going to be the same when we have continuity of the second derivatives. Well, to be more precise, every time that we have continuity of the second derivatives, we're going to have that the combined derivatives are going to be the same, whether you do x first and then y, or y first and then x. If this is the case, then we have what I would call a true concavity. Okay. And I'm making that up. This is not universally used. I'm just calling it myself a true concavity if this happens, which means we have a maximum or a minimum. By the way, we may not necessarily assume that here we have a minimum because this is a three-dimensional picture. This could be going this way, but then on the sides, perhaps this is going down. So it's going up this way. We have a concavity going up, but then perhaps we have a concavity going down the other way. And so that would make it a saddle point, but we don't know that. We wouldn't necessarily know that. So what is clear in this picture is that we have a maximum, and then here it depends on what's going on. I don't know if this is going deeper, under the sheet, or we don't know. So here we have a true concavity. Once you establish we have a true concavity by this, then all you have to do is check one of those two to see if we have a maximum or a minimum. So what this inequality establishes is that we have a bottom or a top, because we have a concavity that is well established, well defined, nicely all around. Yeah. If, on the other hand, we have the opposite, we have to be careful when we say opposite in math. If we have the reverse inequality, f sub xy, f sub xy, yep, then we don't have a concavity. Then no, let's put a then here. Then no, true concavity, which means that we have a saddle point. Yeah. Here we will have either a maximum or minimum after, though, establishing that the first derivatives, partial derivatives, are equal to 0. By the way, another way to say this is to say that the gradient of the function is equal to the 0 vector. That's just a side note. Yep. If fxx, fyy is equal to fxy, fxy, then we don't know. We do not know what's going on. We just don't know. Now, sometimes students forget to go to the basics. You know, if you have so this is a top view. If you have a point where you could have a maximum or a minimum, and you don't want to do second derivatives or test or something, you can simply go on one path, and we're going to show how to go on paths, or a different path. And if you get that on one path you go down, and on the other path you go up, then you know we don't have a maximum or a minimum. But then we encounter the same problem as with limits. If you go in different paths and then all of the paths go down, then we cannot prove, we cannot establish that we have a maximum. We just don't know. We would have to do something like this. Yeah, because there could be some path that goes differently. Okay, so this is the test. Remember, if the two multiplied together are greater than the combined multiplied together, then we have a true concavity. And then once you establish that we have a true concavity, all you have to do is check one or the other, because that means that both are going to be positive. These two quantities are both going to be positive, since this is going to be at least 0. Yeah, this is fxy quantity squared. So either both are positive, and this is greater than or equal to 0, because we are squaring. So either those two are positive or those two are negative. So whatever the sign of one is, the other will follow suit. And if both are positive, that means that we have concavity going up. If this is the case, then we gotta watch out. This doesn't imply that we have a negative number. That doesn't mean that this one will be positive and this one will be negative necessarily. It simply means that this is not strong enough. The concavities in both directions are not strong enough than the combined concavity. That's essentially one way to say this. But if the two direction concavities are stronger than the combined concavity, then we have a true concavity. All right, let's do some examples. I think it's fascinating to be able to find maximums and minimums in 3 dimensions. Examples. Well, example 1. So erase the plural, the S. So we're going to start out with f of x, y equals x squared plus y squared minus xy. So we want to know whether we have a maximum or a minimum, or what the deal is about this function. So let's find critical values, just as we do in Calc 1. So the gradient is going to be 2x minus y, comma, and then 2y minus x. And we are going to force, we want to match this equal to 0, 0. Okay, so we want that in order to end up with a critical point. Just like when you are doing in Calc 1, the maximum, when you're finding the maximum, you set the derivative equal to 0. It isn't like the derivative is always equal to 0. In this case, the gradient is not always equal to 0. Sometimes it is, and sometimes it isn't. So for instance, in the point 1, 1, the gradient will be 1, 1. That is coincidental. In the, yeah. Um, hmm. Oh, that is interesting. The derivative 2, 2 would be 2, 2. So if x is equal to y and both positive, it looks like we end up with the same, the gradient is the same as the point. Anyway, I'm going on a tangent here. So we can set the system of equations 2x minus y is equal to 0 because the first coordinate has to be equal to the first coordinate. Second coordinate has to be equal to the second coordinate. 2y minus x is equal to 0. We can multiply this equation by 2 times 2. So we end up with 4y minus 2x equals 2 times 0. And then we can add those two equations. And let's put the result over here. So 2x, and then we're going to add negative 2x. So we end up with the x's canceling off. And then 4y, we're going to add negative y. So we end up with 3y. 3y equals 0 plus 0, so 0. And then we can divide by 3. So y has to be 0. And if y is equal to 0 in this equation, or either one of the two, if y is equal to 0, then that forces x to be 0. There, here, this is easier. If y is equal to 0, negative x is 0, which means x is 0. So x equals 0. So the critical point is going to be 0, 0, 0, 0. I don't think I'm going to do examples where there's more than one critical point on this video. There are examples in places and books and other places where there are more than one critical point, in which case you have to test each one of them individually. But the examples we're going to show here have only one. So what happens here? Do we have a maximum or a minimum? It looks to me like that's going to be a minimum because these numbers can be pretty big. But we don't know. We don't know until we test. All right, so let's find the second derivative with respect to x. The first derivative of this function with respect to x is 2x minus y. The second derivative with respect to x will be 2. The second derivative with respect to y will be, the first derivative is 2y minus x. Second derivative is 2. And then we need to find the combined derivative, fxy. So find the first derivative, which is 2x minus y. The second derivative, well, that is the derivative with respect to x. But now take the derivative of that with respect to y, and that's going to give us negative 1. So what we want to do is compare f sub xx, f sub yy versus f sub xy squared. If this is bigger, if this product is bigger, then we have a true concavity. If this guy is bigger, then we have a saddle point than that. So we compare. If they're equal, then we don't know. So that's going to be 2 times 2 versus negative 1 squared. So that is, of course, 4. And this is negative, but then we're going to square it, so we end up with a positive number. So this is bigger, which means we have a true concavity. I'm making that up. We have a true concavity of the surface, but we don't know which way now. That's because it could happen that those two are positive or those two are negative, although we are witnessing, we clearly see that they're both positive. So that means that we have concavity up, true concavity. And we can, because those numbers are positive, since f sub x, x is greater than 0, and so is f sub y, y, then surface is concave up. And if we have a surface that is concave up totally, that means that we have a minimum. So f equals x squared plus y squared minus xy has a minimum of, so we gotta say how much the minimum is. Well, if you plug in 0, 0, you end up with an output of 0 at 0, 0. So this is the z value, the z output, and this is the xy input at which it happens. So this is output, and this is input. Yep. It turns out that this graph is it's a hyperbolic paraboloid. So it has a minimum of 0, 0, and then it keeps going up. So that is our first example. Our second example is going to be similar. Example 2. What if we have f of x, y equals x squared plus y squared minus 3xy? So our first example has x squared, or is about x squared plus y squared minus xy. This new example is x squared plus y squared minus 3xy. That makes a difference, a huge, huge difference. Okay, so we want to find critical points. So we set the first derivative equal to 0. The first derivative is 2x minus 3y, and we set that equal to 0. First derivative with respect to y will be 2y minus 3x. This equation is pretty symmetric with respect to x and y, so we end up with similar things going on here. By the way, I wrote this a little differently. It's not, so instead of putting f sub x and f sub y one above the other, here I put in next to each other because I'm just looking at the gradient. And here I'm looking at the partial derivatives individually. Same thing, I'm just writing. And then instead of writing 0, 0 as a vector, I'm writing 0, 0 as two individual numbers. So they're the same thing. I mean, so how do we figure out what x and y should be so those two happen at the same time? Just as we did with the previous one, we can multiply this one by, let's eliminate, we can multiply by 2. So multiply by 2, and we get 4y minus 6x equal to 0. And we multiply this by 3. And so 6x minus 9y equals 0 times 3. We add the two equations, the 6x's cancel off, and then we have 4y minus 9y, so negative. When we add the two equations together, negative 5y is equal to 0 divided by 5, or negative 5, and so y has to be 0. As soon as we establish that y is 0, this equation forces x to be 0, because if y is 0, we're doing 2x equals 0, so x has to be 0. So from here, we know that x has to be 0. So again, we end up with a point 0, 0. So that's our main point. And again, in this video, we're not going to have examples where there are two critical points. It does happen often, not too, I don't know, it happens regularly that we have a more than one critical point. But again, we want to find the second derivative because we want to test. We don't know whether we have a maximum or minimum saddle point. So second derivative, with respect to x. That was the first derivative. Second derivative would be 2. Second derivative with respect to y. There is y derivative, the first derivative, partial derivative. So the derivative of that with respect to y is 2 again. This looks similar to what we have on example 1. We had 2, 2. Now let's look at the combined derivative. So fxy would be, all right, first derivative with respect to x. Now take the derivative of that with respect to y. And that is going to give us -3. As opposed to in the previous example, example 1, we had -1. Interesting. So we want to compare f sub x, x, f sub y, y, with f sub x, y, f sub y, x. Notice that I'm writing this differently. We have the x, y, and y, x. Let's just do that for the fun of it. If you find the derivative with respect to y, and then with respect to x, of course, we're going to end up with -3. If things are continuous at that point, and they are because we have a polynomial, there's nothing that could go bizarre than us, then the combined derivatives are going to match. There's a theorem, Claris theorem, that establishes that that is true if we have continuity of those two. Anyway, we want to compare those two, so that is 2 times 2 versus a -3 times -3. So 9 beats 4. So we don't have true concavity. And if that's the case, then if we don't have a true concavity, then we have a saddle point. Yeah. So F has a saddle point at, well, a saddle point of 0 at, so that is the Z output at 0, 0. So we do have that situation. Kind of like that. I don't think it curves that fast. I think it's a little more planar. It curves away, but not as drastically. But here, in a different direction, we're going to go down. Yep. So that's what's going on. Yep. So that is example 2. Let's do a third example. Example 3. F of xy is equal to x squared plus y squared minus, so example 1 had 1 xy. Example 2 had 3. Let's do 2. So in example 1, we had a coefficient of 1 here. In example 2, we had a coefficient of 3. In example 3, we have a coefficient of 2. So the coefficient is not matching the example only for the first one, but not for the other two. I should have planned that a little better, but that's okay. So the first derivative with respect to x is 2x minus 2y. First derivative with respect to y is 2y minus 2x, and we want that to be 0 and that to be 0. Notice that if we move the 2y over, what this is saying, and divide by 2, what we're saying is that x is equal to y. And here we don't gain any more information. This equation also says that x is equal to y. So all the points, all and every one of the points where x is equal to y, so this is the x-axis, this is the y-axis, and all these points, we're going to have a critical point. If x is equal to y, let's see, x squared plus x squared, because if they're equal, we can change that with an x, so x squared minus 2x squared. Oh, well, that's going to be 0. So those points are going to be critical values. And they're all going to be on the floor. They're going to be on the xy plane. All of those points. Okay. So the question is, what's going on? Are we, I mean, okay, so we got critical values, but are we have a minimum? Do we have a maximum? What is going on? Let's see. The second derivative with respect to x will be 2, as in the previous two examples. Second derivative with respect to y is going to be 2. There you go. The combined derivative, x, y, will be, so derivative with respect to x is that, derivative of that with respect to y will be -2. And similarly, f sub yx, comma, is equal to -2. And so when we compare f sub x, x, f sub y, y, versus f sub x, y, f sub y, x, we're going to end up with 2 times 2 versus -2 times -2. So we end up with 4 equals 4. Whoops, not 0. Equal, and they're equal, which means we don't know. This test does not tell us what is going on. So we have to now use a little bit of common sense and see, well what happens if x is different than y? If x is a little more than y, and I'm going to explore right now. Let's say, so they're not equal. So when they're equal, we have this. If x is bigger than y, so let's put a line and say, what happens if x is bigger than y? You know, so let's say x plus. So if one is bigger, that means that y has to add something to itself to match x. So x is equal to y plus a number. I'm just looking at a random number, a. That's the first letter that came to my mind, because that's the first letter of the alphabet. So are they equal? No, but one is bigger. So let's see what happens to that if that situation. So f would be, well, x squared. That x squared is y plus a squared plus y squared minus 2 times x is y plus a. I want to put everything in terms of one of the letters, not the other. And hopefully that will tell us what's going on. And then, and by the way, since x is bigger than y, this a has to be positive. Minus 2y, I'm missing something. That is x squared, y squared, minus 2x, y. Okay, let's do some algebra. So that is y squared plus 2ay plus a squared. If you cannot fold that out, shame on you. No, I'm joking. That if you forget, that happens to all of us. Y squared minus, and then 2y squared minus 2ay. 2ay. I just want to see what's going on with this. When x is not equal to y. We know when x is equal to y, we have critical numbers and the output is going to be 0. So yeah, f of x is going to be 0. But what happens when they are different? Well, I'm establishing the difference by adding 1. And there's no systematic method to go about this. Here is where we start using a little bit of ingenuity and critical thinking and creativity. A lot of people think that in math there is no creativity or in critical thinking. Well, that's not true. That's totally false. Anyway, so y squared plus y squared minus 2y squared, that's 0. So we end up with 2ay plus Oh, 2ay minus 2ay is equal to a 0. So the only thing that survives is a squared, which is positive. Okay, so when x is not equal to y, one is bigger than the other, we end up with whatever the difference is. So if we deviate from here and we go, you know, if 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 we go here, that means that a is this distance. Then this is going to go up by that much. The function is going to go up by that much. So here is 0, and here we're going to go up by the square of this distance. So what we end up doing, I'm going to try to do that here, is that we're going to end up with, because a squared is the difference, and that is a parabola, we end up with parabolas hanging up this way, a bunch of parabolas going in this direction. But again, that takes some work. And if y is bigger than x, the situation is completely symmetric because the equation is symmetric with respect to x and y. So you're still going to end up with a squared in either direction. And that's how we end up with this kind of parabola. But again, that takes some analysis, and that's the whole point. Math is not only about punching in numbers and getting an answer out. There's one more thing we have to do. So we know how to find maximums or minimums, but if the domain is all of the plane. So if domain is all of r squared, we proceed as examples 1, 2, 3. Okay, but what happens if we don't have a domain that is all of the plane? What if we restrict the domain? For that, I'm going to go back to example 2. Okay, so this was example 2. We're going to make a new example out of this. We're going to label it example 4. And then we're going to have an example 5. And that will be this lesson. So example 4 will be xy equals the same thing, which we already know has a saddle point at 0, 0, but we're going to add a restriction. We're going to add that the magnitude of xy has to be less than or equal to 1. So comma, and then this. So we want to find the absolute maximum and minimum in this situation. Yeah, we want to find absolute max and minimum. Now, we did say that we had a saddle point. I'm going to draw it this way, even though that's not a completely it's accurate in the sense that this picture is accurate in the sense that we have going up and going down, but I don't know about how much this arcs. I don't know how this bends. It may not bend as sharply as this. It may be a little more flat. But anyway, we have this kind of situation at 0, 0. But what we are doing is cutting the domain on a circle on the bottom. So this circle, when we map the circle onto the surface, we're going to end up with this kind of situation, and it's going to go around the other way. So we're going to have a minimum. So on the original surface where we had all the real numbers squared, we don't have a minimum because this kept going down and forever. But here, when we restrict to this circle, this is a circle of radius 1, then we will have a bottom and we will have a top. Now, I'm not, I don't know which way the x-axis goes, the y-axis goes. I'm not I'm not thinking of the word. Um, anyway, it'll come back to me. Um, we don't know which direction X and Y. What I do know is that we have a saddle point, but I don't know if this is facing us or to the right of us. Anyway, this is going up and going down this way, but we want to know what is the minimum and what is the maximum. Okay, so we know at 0, 0, let me look at a top view. So this is the domain. At 0, 0, we have a saddle point. So at somewhere we go down, some other ways we go up. Where do we go up and where do we go down? So what we want to do is form an equation for this path going around this way. Yep, on the domain. So the equation is going to have a parameter t, and because we're using a unit circle, we have a very, very straightforward way of describing the circle. That is going to be cosine of t, but by using trigonometry, sine of t. So this is going to be our x and our y on the border of the domain. And we're going to plug that onto our function. So f of x, y on the border. So I'm not going to worry about the inside of this. I'm just going to worry about the border because I know the maximum or minimum will be at the border. Remember in Calc 1, if you have a closed interval domain, something, I don't know, like this, and you want to find, so it starts at a point and ends at a point. If you want to find the absolute maximum or minimum, actually, yeah, what we find is the critical numbers, see what happens there, okay, and then we find the outputs at the extreme values. This output beats this one, so that would be our absolute maximum. This one, on the other hand, beats this one, so that would be our absolute minimum. So after looking at the critical numbers, which there's only one, nothing exciting happens anywhere except on the borders. So this would be the border, the two borders, the 2 points in Calc 1. Here, the border in multivariable calculus is all of this. So that's why we have to describe it with some kind of function. All right. So on the border, our function becomes a function of t. This is just on the border. It's really x, y, but this is going to be our x and that's going to be our y. So we're going to have cosine squared t plus sine squared t minus 3 times cosine t sine t. Of course, cosine squared plus sine squared is going to be 1 minus 3, and I'm going to multiply by 2 and divide by 2. I'm going to switch the sign. This is a multiplication, so commutative property applies. So we have sine of t, cosine of t. And the reason why I'm doing that is because I want to simplify this using trigonometry. All of us would know that this is negative 3 over 2. Keep the 3 and the 2. But that is actually the sine of 2t. And we know how the sine of 2t behaves very, very well. You can use calculus, or you can think the frequency increases by 2. So we have a whole cycle by the time you end up with pi. Because typically, normally, the sine will go from 0 to 2 pi, but we're increasing the frequency. So that is just the sine of 2t, just this part. This is the graph of it. Flip it around because of the negative. Okay, so I want to analyze 1 minus 3/2. So pretend f of t equals 1 minus 3/2 sine of 2t. And again, just the sine of 2t would be this, stopping at pi, going up to 1 and negative 1. Multiplied by negative 3/2. The negative flips the function upside down. So -3/2 sine of 2t. We're going to go down and then up and down, and we end up on pi here, and this gets stretched by 1.5. So this is 1.5 and -1.5 on the bottom. And then we're going to shift this up because of this 1. So f, which is 1 plus this function, we're going to shift everything. So this 1.5 will be 2.5. This bottom is -1.5. When we add 1, we're going to end up with, so the graph is going to look like, so there is the middle point. We're going to go down, up, and then back here. So by the time we get to pi. Okay. So pi, t. Now let me just think about this real quick, because in our original boundary, t goes from 0 to 2 pi. So t goes from 0 to 2 pi. And that means that here, t also goes from 0 to 2 pi, which means that this is going to cycle again and come back to this point. So we're going to achieve the maximum. So f, the f in example 4, mind, example 4 is this function, the same one we had in example 2, except that we're restricting the domain. Nothing exciting happens at 0, 0, because we have a saddle point. On the boundary, though, we do have a maximum. The maximum will be 2.5. So f has a maximum of 2.5. Why? Because we had 1.5 and then we added 1. And then we have to say where. At, okay, I got to do a quick computation here. The maximum happens when t is 3/4. So this would be 1/4 to 3/4 of pi. So 3 pi over 4. And it will happen again. Man, I have to think about this. The unit circle. So 3 pi over 4 would be here. And it will happen again. Well, a whole cycle again, so it will happen again there. So those two are the points where we have a maximum. So they will happen, and we know this is the unit circle. So this point, 45 degrees, because that's 45 degrees off the x-axis, will be 1 over the square root of 2 at 1 over square root of 2, comma, rather, 1, -1. 1, -1, and 1 over the square root of 2, -1, 1, -1, 1. So that is the maximum of the function. The minimum of the function will happen here, and it will be f has, and here I forgot to mention that this is absolute. I'm going to come back to that in a moment. Has absolute, we don't need the a, minimum of -0.5 at, and that will happen here, 1/4. So that happens there, the minimum. This is the maximum, minimum, maximum, capital, lowercase, at 1 over the square root of 2, 1, 1, and 1 over the square root of 2, -1, -1, which is this way and that way. How do I dare to say that we have an absolute value? Because the only exciting thing that could have happened is 0, but I know the output is 0, and 2.5 is above 0, and -0.5 is below 0. So that has to be the absolute maximum. So what we have is sort of like a pancake And if you lift, so start with a pancake, and if you lift two sides, it's going to go up, and then lower the other side a little bit more, and then the other side. This is a bad picture, but it's kind of like this. Just lift up on two sides, push down on the other two ends, and we end up with the maximums and the minimums. Yeah, that's a bad picture because um, we end up with maximums and minimums, but then we have a saddle point in between. Yeah, so, yeah, but this is kind of circulish. Yeah, kind of like that. There we go. Yeah. Oh, it's there's like a banana shell. If you open it, that's kind of what we have. It, yeah, a little prettier than a banana shell, but that's what we have. Let's quickly start at least example 5. This is an important example. Um, f of xy will be the same thing, x squared plus y squared minus 3xy, which we know has a saddle point at 0, 0. But we're going to include domain. The magnitude of the absolute value of the axis is going to be 1, not greater than 1. And the absolute value of the y's is also not going to be greater than 1. This is a square on the domain that is 2 by 2. So the x's and the y's cannot be more than 1, but both, this one could be 1 and this one could be 1 as well. So that creates corners here. So 1, 1, that would be -1, 1, -1, -1, and 1, -1. All the four corners of this square that is 2 units long by 2 units wide will be. And then the surface is on top of this surface. So let me try to draw a different kind of picture. There. And boy, this is a weird picture, but pretend you are taking a square and then going up the square. So who knows where this goes, kind of like this. Oh, maybe like that. So instead of being pancake, pretend you have a square pancake, not a round pancake, and then start lifting some of the ends and see what happens. Okay. So at the top view of this is going to be a square. Okay, so there's the x-axis, there's the y-axis, top view. All right, and the problem compared to this previous example is that in the previous example, we were able to go smoothly around the circle with cosine and sine. In this example, we cannot go smoothly around the square. We have to do 4 paths. So perhaps this path is 1. I'm going to call this P1 for path 1. And then we're going to go, eventually we want to go around in the same direction, but for purposes of this example, we don't have to go around. So we can go up again in path 2. And then this is going to be path 3. And this is going to be path 4. Later, when we do line integrals, we want all the paths to go in the same direction. So path 1 and then path 2 has to go the other way. So perhaps we will do the negative of that, and then the negative of that, and then this one correctly. But right now, for purposes of just finding where the maximum and the minimum are, we don't have to go all of them in the same direction. So this is a problem that it multiplies into 4 smaller problems. I want to find the maximum here, the maximum there, the maximum there, the maximum there, and the minimum on each one of those, and then compare all of those. Okay, so path 1, how do we know we have path 1? Well, the x value has to be 1, because all of those points have a 1 on the x value, and the y value varies from -1 to 1. So x is 1, and y varies from -1, 2, 1. That's path 1. Path 2, which is, I'm labeling path 2 as this, but that was arbitrary. X is negative 1, and y goes from negative 1 to 1. Path 3, y is going to be 1, and x ranges from negative 1 to 1. And path 4, y is negative 1, and x still ranges from negative 1 to 1. So we really have 4 sub-problems, and we have to analyze. It gets tedious. I shouldn't say tedious. It gets complicated because now there are more than one boundary. I'm splitting the boundary into 4 boundaries. And so we have to analyze each one of those differently. Yeah. If we were talking about a country, pretend that is ocean, so you deal with those differently than land and land, perhaps. Just a silly analogy. So path 1, how does the function behave? F, well, all the x's are going to be 1, 1, 1. Y is going to be y squared minus 3 times 1y, minus 3y, which is, by the way, so at this point, this looks like something that we have seen in pre-calculus. This is y times y minus 3, which is a parabola that opens up, and it has x-intercepts of 0 and 3. So if we graph this, so this is y and this is f, so 0 and 3, and we have a parabola opening up. So we have, now, I'm using knowledge from algebra 2 or intermediate algebra where we know parabolas really well and the outputs of parabola. Mind that y goes from negative 1 to positive 1. And I know the minimum because it's in parabolas are symmetric with respect to the vertex or the axis of the parabola. So we know we have a maximum here and a minimum there. Okay, so we have, on this path, we have a maximum when y is negative 1. So negative 1 squared is 1. Negative 1 times 3 is positive 3, plus the 1 is 4. So we have 4 when y is negative 1. So here we have an output of 4. I'm going to label it. And we're going to have a minimum when y is 1. So when y is 1, we're going to have 1 times 1 minus 2, rather 1 minus 3 is negative 2. So we have negative 2 here. The output of the function is negative 2. The output of the function here is 4. And in between, we slide from negative 2 to 4. Watch out, because sometimes in quizzes or tests, I give problems where the maximum or minimum does not happen on the endpoints. Yep. So path 1, we know what's going on. Path 2, f is equal to, okay, so now in path 2, x is negative 1. So that is negative 1 squared, still 1. Y ranges, and then this becomes negative 1. So that causes those two negatives to add 3. So we have I'm thinking whether I missed something here. I think I missed a 1. This was 1 plus y squared minus 3y. I did miss a 1. I notice here. That's going to be a fairly easy fix, plus 1, or 1 plus, either way. Because when x is 1 and we squared, we don't lose it. It is still 1 plus y squared minus 3y. That's easy to fix. That means that this graph, we don't have to undo this graph. This graph just got shifted up by 1 unit. So that means that the output here is not 4. It should be 5. The output here should not be negative 2 should be -1 instead. So I was able to save that, to salvage that. All right. And the reason why I realized that, by the way, the maximum was there, the minimum is here. All right. The reason why I realized that is because now I'm going to plug in -1. So -1 squared is still going to be 1 plus y squared. And x is -1. So -1 and a negative here make a plus 3y. I'm going to, well, that kind of works out nicely because don't worry about the 1 yet. And factor that out. So we have y times y plus 3. And again, we're going to use our knowledge about parabolas. So neglect the 1. Pretend you don't have a 1. We're going to shift by 1. So this is a parabola that goes this way from -3 to 0. And this is assuming that this is the y-axis. This is the f-axis because that's the function. But we are not going to look at the whole parabola. Y only goes from -1 to 1. See, this requires a lot of analysis from -1 to 1. And I know the lowest point happens when y is -1.5 because this is 3 and there is symmetry. So we're going to have a bottom here and a maximum there. And we have a smooth transition from bottom to top. So at -1, we will have -1 times -1 plus 3. So that is 2 times -1. That is -2 plus 1 is -1. And that happens here, -1. And we're going to have a maximum when y is 1. 1 times 1 plus 3 is 4, plus the 1 is 5. So it appears that we have maximum, maximum, minimum, minimum. I'm going to let you figure out, do the same procedure when y is 1 and x is free to range from -1 to 1. You should end up with the same, I anticipate, although I have not done this ahead of time, I anticipate you're going to go and end up with -1 and 5 also. So assuming there's, what could happen though, is that this hangs even lower. We end up with a value somewhere in between that is, say, -3, or some value in between that is 8 or something bigger than 5. You know what, let's do one path because now I don't want to leave you hanging in there. So path 3, that's when y is equal to 1. When y is equal to 1 and x is free to go from -1 to 1. Oh, never mind. This equation happens to be completely symmetric with respect to x and y. In other words, if you exchange x's with y's and y's with x's, we end up with exactly the same thing. So the same situation will happen, the same kind of parabola, and we are correct. So never mind this. Well, P3 and P4 will behave similarly. Well, it's not that, that's incorrectly written statement. F will behave similarly on the paths 3 and 4 by symmetry of f with respect to x and y. Yeah, we're just going to repeat the same thing over again. So the conclusion is, okay, so we want to find all the absolute maximums and all the absolute minimums of f. So the conclusion is that f has an absolute minimum of -1. Remember, those are the two outputs we end up with here, at 1, 1, and negative 1, negative 1. We can put that as a bullet, a second bullet. F has an absolute maximum of 5 at, well, the other two corners. 5 will happen 1, negative 1, 1, negative 1, and a negative 1, 1. And we know that at 0, 0, which was the other exciting point, nothing is happening. We don't have an absolute maximum or minimum. That's a saddle point. And on top of that, the output at 0, 0 is 0. And 5 beats that above it. Negative 1 beats 0 below it. So that means that nothing is happening really at 0. 0 is not transcendental as far as, it's not important as far as absolute maximums and absolute minimums. I just want to compare real quick with what we had here, because we had a maximum. Yep, the maximum was 2.5 within the circle. Okay, so this is what's going on. If you restrict according to the circle, we're going to find maximums here and there of 2.5. If you go past that to the square of 2 by 2, then you're going to have maximums here of 5 and 5, which makes sense. If you go, so that means that the graph is going up 2.5 and then 5, and then it is going down. Comparing, I want to see what the minimum was. Oh, it was 1 over the square root of 2. So over here we have a 1 over the square root of 2, and then over here we're going to have negative 1. Was it 1 over the square root of 2? Nope, negative 0.5. I lied. That was the distance. That was the coordinates. This is negative 0.5, negative 0.5, the output. The output here was 2.5. Now that is interesting because it is exactly half. The output, if we go all the way to the corner of the square, is going to be negative 1. And while here it is 5. And then we have similar situations on this 5. 2.5 is the output, negative 0.5 and negative 1. And those are the absolute maximums on each one of those. Those are two examples, by the way. The square is example, refers to example 5, and the circle refers to example 4. And then example 2 is all of the plane, where there is, because this just keeps going up. So based on this, I have more information about how, so the behavior of the graph is that if you go diagonally, on the, yeah, this is 1, 1. So if you go on the X, Y diagonal, the graph is going to go down. But diagonally the other way, the graph is going to go up. So now we have more information about the orientation. That's the word I was looking for a little while ago. The orientation of this graph. So it opens up as you go between the negative x-axis and the y-axis, and it goes down between the positive x-axis and the y-axis, and then up again between the positive x-axis and the negative y-axis, and so forth. All right, this is it for this video.